All right, welcome to the third video on regression. Sorry if that last one went off the rails a little bit. You know, I have a lot of opinions. I wrote a whole book, right? Okay, but in this video, we're going to be talking about something a lot more straightforward, and that is how to read a regression table. And also, I'll be talking a little bit about the model fit statistics that you might typically see at the bottom of a regression table. What is a regression table? A regression table is just a table with the results from a regression on it. It's a very common way of presenting regression results that is very compact and easy to read, and also allows you to compare a bunch of different models all at the same time. And they can all be read in very similar ways. So we're going to talk about that here. So here is an example of a regression table. I've got two regressions here. I've got two columns. Each column represents a different regression that I have run. That's a very standard way of presenting regression results. If you have multiple different models, to put each one in a different column. Along the top, you can see that I've listed what the dependent variables are, what I am predicting, my Y variable in my model. So in this case, both cases, it is inspection scores from restaurants, so health inspection scores. In the first column there, you can see the names of the variables that I'm using as predictors. So the first thing you see there is intercept, and depending on the table that you're looking at, this might also be called like constant or something like that. Or if we are writing out the regression equation, maybe this would be beta 0 or alpha. And what this is just the intercept or beta 0 term from the regression model. If we go down a little bit, we can see the names of the predictors or independent variables that I'm using in my model, my X values or my Z values or what my controls are. I've got two different ones here. I've got the number of locations that restaurant happens to have for like chain restaurants. I've also got the year of inspection, the year in which the inspection took place. You can see that in that first model, I'm only using number of locations as a predictor because there's nothing in the years of inspection section there. Over on the right, I am indeed including both of them as predictors. So let's look, in fact, at those values that we have there. So let's focus on the negative 0.019 that we have in that first column. So there's three things going on there. So the first thing that you see is the negative 0.019. This is the first number that you would typically see in a regression table, and this is the estimate. This is the estimated coefficient. So if I were to write out a regression of y equals beta 0 plus beta 1 times number of locations, then this is our estimate of beta 1. This is our beta 1 hat. We estimate that the slope on number of locations is negative 0.019. That's the first number that we see. The second thing that we see is down below in those parentheses. We see the 0.000 right there. Now, these are standard errors. Now, there are two typical numbers that you might see as estimates of sort of sampling variation. And typically, you would see some sort of estimate of sampling variation in a regression table. In this case, we are showing standard errors, but you might also sometimes see t-statistics used here instead, which are the coefficient that we have divided by the standard error. Now, which one are we getting to see here? Hopefully, in a lot of tables, there might be a little table note that says whether you're looking at a standard error or a t-statistic or something else. In this case, there's no table note, so we have to sort of figure it out. One way that you can figure it out is if the significant coefficients tend to have small values, that's probably a standard error. And if the significant coefficients tend to have large values in those parentheses, then you're probably looking at a t-statistic. How can you tell if they're significant? We'll get to that in a second. But we can see here that the standard error on our coefficient, the standard error of beta 1 hat, is very, very small. Here it actually says 0, 0, 0. It's just 0. It can't actually be 0, so if it just says 0, that typically just means it's so small that it's below the smallest value that I'm willing to show you. So that's what we have for our coefficient and our standard error. The other thing that we see here is those stars. See those asterisks there? Those are called significant stars, and they are very commonly shown on regression tables. In this case, we see 3 of them, and we might wonder, well, what does 3 stars mean? Well, these are representations of the p-value. We talked in the last video about the p-value, the probability of getting a result this extreme or more extreme given a certain null hypothesis value. Now, by default, in pretty much all regression tables, the null hypothesis we are testing against is that this coefficient is 0. So we think if the slope on number of locations was in fact 0, we can construct a sampling distribution of that coefficient that is centered on 0 and has a standard error of, in this case, roughly 0 as well. And we can ask ourselves, how unlikely is it, given this sampling distribution, that I would see an estimate of 0.019 or even farther away in either direction? And the probability here is the p-value, right? That's what the p-value is. It is the probability of getting a result as strange or as far from the null or farther in either direction for a two-sided test under the assumption that the null hypothesis value is true. In this case, the null hypothesis value is 0. So we have the p-value. and those stars are a representation of the p-value. So if you look at the table, the little note below, you can see that a single star indicates that the p-value is less than 0.1, that there is a 10% chance or less of getting a value that far from the null or farther under that null sampling distribution. 2 stars here indicates that the p-value is less than 0.05. 3 stars indicates that it is less than 0.01. Now, which stars correspond to which p-value levels differs a little bit depending on field. I've used these ones that are standard here in economics, but in other fields you might see that a single star is more common for 0.05, 2 stars for 0.01, 3 stars for 0.001, and so on. So you generally want to look for a table note that will tell you what these significant stars mean exactly. So we can think of these as representing the p-value. So if we look at the fact that there are 3 stars, this tells us that the p-value here is less than 0.01. So that is statistically significant if we had picked a cutoff value of 0.01. So you can sort of read these in reverse also as saying, if I had picked a p-value, if I had picked a cutoff value to declare statistical significance of 0.01, then I would indeed be significant for this coefficient because I see 3 stars, and that is the number of stars that correspond to this cutoff level. It would also be significant at the broader levels, right? So if the p-value is less than 0.01, then it is also less than 0.05. That's why these asterisks sort of stack. Because if you have 3 stars, that also implies that you're significant, not just at 0.01, but also at 0.05 and 0.1 and every bigger number as well. So that's how we can read a sort of single cell here for a regression table, right? We have our estimate, negative 0.0019. We have our standard error, or sometimes t-statistic, in the parentheses there, 0.0000. And we have our asterisks, which indicate the p-value, or at least a range of p-values that we might have. So here we know that the p-value is less than 0.01. Depending on how the regression table is structured, you might not always see those standard errors below the coefficient. Sometimes they are to the side. And that just sort of depends on how people decide to put those things together. That also works perfectly fine. In the second column here, we can see the exact same procedure repeat itself with the second predictor, the year of inspection. We can see an estimate of negative 0.065. We can see that the standard error is 0.006. And we can see that the p-value is somewhere less than 0.01. So that's how we can read the individual coefficient entries. How about if we look below to some of the summary statistics about the regression? This is a common thing that you will see in regression tables, just some information about the regression itself. The first thing that we see is the number of observations. We see that this regression was estimated using 27,178 observations. We also see some what are called model fit statistics below. These are statistics that are some sort of indication of the quality of the model overall. They're not related to specific coefficients, like the standard error or coefficient or p-values that we have above. They're related to the model as a whole. Here are 3 ones that you might commonly see. The first one is R squared, represented here as R2. What R squared is it is the correlation between the predicted values of our outcome and the outcome itself, and then you square that correlation. You might think, well, what is that? Why are we doing that? Well, it sort of represents the proportion of the variance of the outcome that we have explained with our model. And so if you think of the inverse of it, so here our R squared is 0.065. If we do 1 minus that, that'd be what, 0.935, something like that. What that's saying is, if we divide up our outcome between the stuff that we have predicted with our model, using the number of locations, and the stuff that we have not predicted, the stuff that's left over in our residual, then 93.5% of the variation is over here in the stuff that we have not explained, and 6.5% of the variation is over here in the stuff that we have explained. So it's sort of a way of partitioning how much of the outcome variable is explained by the stuff in the model versus out of the model. So R squared is a number that gets misused a lot, very similar to hypothesis testing in general, as we talked about in the last video. But some things I want to be clear about with R squared. First of all, R squared is simply a measure of how much of the variance have you explained with the model and how much have you not. That's all that it is. It does not tell you how good the model is. And in particular, in this book especially, we are mostly focused here on causal identification. We want to estimate a single parameter very, very well. My concern is that 0.019, whether that reflects the causal effect of number of locations on inspection score or not. That's all I care about. I don't care that there's a lot of other stuff going on in inspection score that I haven't explained, right? That simply does not matter to me. So the R squared value being 0.065 or whatever is not a concern, at least for what we are doing. And so, I mean, it might be a concern if, like, I thought that I really had all the stuff that was important for inspection score and it turns out that there's not. But in general, it's just not that important. And you definitely, super clearly, definitely don't want to change your model in attempt to make the R squared value go up. So in general, you can probably ignore R squared almost entirely in this book overall. It's just not answering a question that we are particularly interested in. I mean, take an extreme example, a randomized controlled experiment where the causal identification is very, very easy and very, very clean, often will have a small r-squared value because there's simply a lot going on in the outcome that is not explained by the treatment that we have happened to randomly assign, right? In that case, r-squared is bad, but the model is very, very good. Now, if your only goal is prediction, then r-squared makes a little bit more sense to focus on because this is all about how much of the outcome you have predicted with your model. But even then, there are probably better estimates to use than r-squared. So r-squared is a nice little diagnostic that you can look at very quickly and interpret very, very sharply as the sort of share of the variation in the outcome that is either in your model or out of your model, but that's all that it does. Another statistic that you will see down here is the r-squared adjusted. Now this is just taking r-squared and making a slight adjustment to it. R-squared will always go up as you add more variables to it, simply because you have more things that you can use to predict, so you have a little more flexibility, you can fit the data a little bit better. But that will be true even if you add variables that are complete nonsense. And so what r-squared adjusted does is it simply says, okay, I'm not going to ask what the proportion is that is explained in the model versus out of the model. I'm going to ask if the variables that you've included explain more than we'd expect if you just added a random noise, right? That's what r-squared adjusted is about. I actually use r-squared adjusted less than r-squared because r-squared is a lot easier to interpret as that sort of share thing, whereas r-squared adjusted sort of muddles it a little bit. And I'm not particularly concerned about r-squared anyway, so I don't really necessarily care. I've done the work of trying to get rid of the nonsense predictors anyway in my model construction phase. I don't need r-squared adjusted to do it for me. But that is a more contentious opinion, I will admit. Finally, we have the F-statistic. So F-statistic is a form of hypothesis test, basically. And what it does is it says, okay, we've got this model. And we know that this model is predicting better than a model would if we had no predictors in it at all. So if we just were predicting the inspection score with the mean, I just said, here's the average inspection score, I'm going to predict that everybody's going to have the mean value, right? That's a model that I could estimate. If I dropped all my predictors, that's what my model would do, in fact. And so I know when I add predictors, when I add some stuff to the model, it's going to do a better job of predicting than that. I simply, again, have more flexibility. And what the F-statistic asks is, okay, I know that when you added all these predictors, when you added all the predictors in your model, it made you predict better. You explained more of the outcome variation. But is that more than we'd expect given how many predictors you added? It's sort of asking, how much did the share of explained variation go up when you added all these predictors? And is that more than we'd expect by random chance? And the more than random chance thing, that's turning it into a hypothesis test. Our null hypothesis is that all of our predictors have coefficients of 0. And the F statistic is testing basically, well, if all of the coefficients did in fact have coefficients of 0, then how unlikely is it that we would see the coefficients that we do see? And if that probability is very, very small, then we would reject that they're all 0. And that is in fact what this is a test of. And all of these they're good to sort of give you a very quick glimpse of how much of the variation your model is explaining. Our goal is to focus on other things of how well the model can estimate these particular coefficients rather than how much it can explain variation in the outcome. So our goal is a little bit different, but these statistics can still be useful to look at, and they're still useful to have down there as well. All right, so that is how we can read a regression table, the individual coefficient parts, and then also some of the model fit statistics that we see at the bottom. Thank you.